All right, so we had quite a lot of fun with writing the red-black tree. That was our previous stream, and if you want to look at the streams, have a look at my LinkedIn profile or my Twitter or whatever. Lots of different profiles where it's available, also on Twitch. Subscribe to whatever you want. But the red-black tree, we finally got going. As I said, I'm not writing this code myself. I'm doing it with ChatGPT. However, the problem that we ended up having is that a lot of the code was copy and pasted, and I did it deliberately. I said, well, for example, the max depth method looks the same for the three trees that we did. We did the unbalanced tree, the normal simple unbalanced tree. We did an AVL tree and red-black tree. And so the max depth calculation is the same, and I just copied and pasted it between them. But that's not a good idea. We shouldn't be copying and pasting code. So I spent some time looking at the code and wondering how one could consolidate that so we can follow the dry principle, which is don't repeat yourself, rather than the wet principle, which is write everything twice. We don't want to do that. Obviously, if we're being charged, if we are charging per line of code, we'll get a bonus for having it 3 times. But that's not how we should be writing our code. So at the moment, if you look at our 3 binary trees, this one is the AVL tree is 300, roughly 310 lines. The red-black tree is 274, so that's 584, and then the simple unbalanced tree is another 178. So those, what did I say? 500 and anyway, it's too many, right? It's too much in terms of lines of code, and we really want to not have unnecessary lines of code. So we'll just do search for binary tree. It's actually a better way of doing it anyway, because we'll see also the interfaces as well. So altogether we've got 777 lines of code, but there's no documentation in there. And we want to try and reduce this by having less duplicate code. Now, IntelliJ actually has something built in the ultimate version where you can say right-click, analyze, and locate duplicates. And it does a fairly good job of trying to find where duplicates are. So it's found a few here. This one was quite quick because it's a very small bunch of classes. But the moment that it gets larger, it becomes a bit more expensive to do. But for example, they saw that max depth is simply copied and pasted over. So that's 77 cost for each method, for each class, and we should be able to reduce that a bit. The iterators are again copied and pasted over, and I did that, and these iterators actually work as well for the simple case, so we can actually also reduce that. So we should be able to reduce it down from 777 down to hopefully less, and even if it's not less code, at least you're going to have less duplication. Alright, so the first thing I want to do is I want to in order to support max depth and contains, those 2 methods, and iterator, I need to have a node construct, but I don't want to put it in the interface, because if I put the node into the interface, the node for the trees, then it has to be public. I could make it private. I think I can make it private, but that won't help us. It has to be public. And then it's public for everybody who sees a binary tree, which is not really what I want. So I'd rather do something a bit different, which is I'm going to take the simple unbalanced binary tree, I'm going to copy and paste that to an abstract binary tree. Right? That's our simple case. And delete all the comments which don't make sense anymore. And then we're going to say extends abstract extends, that's all stays the same, but this is going to be an abstract class, and this will now have the node defined in there. So we're going to have our node, let's delete what we don't need. We're not going to need the add, we're not going to need the root either, but we will need a way to we will need a way to get the root. So even though we're not going to have the field root inside the abstract binary tree, because for each subclass, we're going to have a different node. We're going to need a method called root. So we're going to need the root method, which is going to be a package access, and also the class is going to be package access. So a package access method, which is going to be abstract. So we're going to have an abstract method root, and we're going to use that root to do the contains and the max depth, and also the iterate we'll do as well with that. So the add we don't need, let's delete that. The contains we are going to use, and here we're going to say contains root the method. So that's going to be overridden by each of the different trees. And then we can even do this, we can even say public final contains, just, and I'll take that away again at the end, just to make sure that if I override this, that I don't override it and also have contains duplicated. The remove is going to be different for each different tree, so I'm going to delete that, and then the find, we don't need that. And here I've got the node. Now the node is not going to be private, it's going to be a static class. Also we can see over here that I've called it T, which is suboptimal. It should be called something else, because otherwise it looks like this T up here, which it's not. It's its own generic type because it's static, so I'm going to just call it E, which I did do in the AVL binary tree. There I called it E, I believe. If you look at the node inside here, wherever that is defined, here it is. Here I called it E. So E is a better approach, to just have a different name for the generic to not get confused by them. And then if we go back to the abstract binary tree, let's say that we don't need these. We can simply have methods for them. So we're going to have node E left. Oh, and this is not going to be a class, it's going to be an interface. It's going to be static interface, which I don't think you need static. I think you can just say interface because it's going to be static anyway. Node, and instead of having all of these methods, we're going to simply have left, right, and value. These three. So it's E value. So these three methods, and then what we can then do, if you look at the contains, for example, where we're saying, where before we access the actual fields, we can now call in the method. So it's going to be current.value, current.left, and current.right, the methods, not the fields. So I've got my interface. It's again package access, so you shouldn't be able to see it from outside of the package, which I'm okay with that. We've got the iterator. The iterator, now something else that I kept in this deliberately is I'm going to keep the mod count in the abstract binary tree. Now this is actually how they do it in the Java util abstract list class. They also have the mod count in the abstract list. So we'll keep it. I don't actually like that very much. I'm not a great fan of it. But I'm gonna, in fact, we could convert it to a method again, a method that's abstract that you have to implement, so that you can keep the mod count in each of the subclasses. But let's just keep it in here for now, for simplicity's sake. Again, here we say inside the iterator, this is the code we had before. In fact, I should use a different iterator. So I'm going to delete this for now, and I will use the iterator from the red-black tree or the AVL tree. They're the same once I get to it. All right. So in fact, let's copy that over, the AVL binary tree iterator, because that one works. I tried it out for AVL tree, for red-black tree, and also for the simple binary tree. So if we go back to the abstract binary tree, now I'm going to just copy that in here, and we're going to have only one place for the, oh, I didn't want to do that, I wanted to just paste it. And so this is my tree iterator. Let's call it the just a binary tree iterator, call it that. And then this all looks very similar. It's going to be the root method. We're going to push the left subtree, first go all the way down on the left side, push all the nodes into the stack, the double-ended queue, And then when we call next, we're going to check for co-modification. If there's a co-modification, we throw an exception. And if it's empty, we throw no such element exception as well. So we're going to say next node right and next node value, and that will give us pretty much the iteration done. So and as I said, this works also for the simple case as well. The max depth, again, we need to have the root being the method, and then again right and let's see, that was city, left and left. So the record is not only inside the abstract class. I don't have to have that repeated 3 times, which of course is really how we should be coding. You don't have copy and paste coding. All right. What else do we have? So we've got, what is first and second? Oh, that's the pair. Okay, so that's fine. All right, so this is my abstract binary tree. I'm going to again make these methods final. So the iterator, the contains, and also the max depth. So these are all final. And let's go to our simple unbalanced binary tree now. And we're going to say, instead of saying implements binary tree, we're going to say extends abstract binary tree. And the only thing we need to implement for that is the root method, which I'll move up a bit. And we're going to make our own node. We don't need the mod count in here. That's being inherited from the superclass. I thought that would be... it shouldn't have private access in superclass. It should be package access. So we'll change that as well. So we'll make it to be package access. And again, that's not really how I would do it generally. I would do it a bit differently, but I'll keep it like that. And then the other thing that I need to do is to get rid of to delete the contains and the iterator method. You don't need those anymore because they've been implemented for us, and the max depth can be deleted, and the pair you don't need either. That's all done. So this node needs to extends or implements the abstract binary tree dot node of t. And again, I should have called this E, so I'm going to rename it to E so that we don't get confused between the different generics. And in order to implement that, we need to, of course, have left, right, and value, return left, and right is return right. And I could probably do this with AI, but I'm just like, this is so easy. Just get it done and be done with it. All right. So this is my private static class node, extends abstract binary tree node. So it's my specialized node. Of course, I could rename it to something else, but I'll keep it like it is. And it's and I think that's all I need to do, except I need to here say return the root. And what I can do is I can simply return node, because node is a subclass of the abstract binary tree node. So therefore, this node is also a valid suggestion here, or a valid return type, because of, what do you call it? The covariant return types. That's right. Covariant return types allow us to do that. So let's run the test and see whether this works. Binary tree test. I'm going to run that again. It should hopefully work. Hopefully it hasn't broken anything. So what I've done now is I've basically pulled the 3 methods up to the abstract superclass, the max depth, the iterator, and also the contains. Now, just want to note, I have mentioned this before, but our iterator is not complete. It doesn't implement the remove method. So if you need that, you need to implement that probably for all of them. But I didn't want to do that. It just complicates it, and it detracts from what we're trying to do over here. So I left it like it is. All right. So let's see. Just want to double check that max depth is also, yeah, everything's final. Good. So we've done the first one. Let's do the AVL binary tree as well. So this should be now a lot easier. We can simply say extends abstract binary tree. We need to have the method over here of root, which returns root. And again, we can just return the node itself. The node will have to say extends abstract binary tree dot node, and it'll have to implement the same methods as before. So here I'm going to copy and paste the methods. I don't have to type them in a second time. I've done that before. And if you wanted to, you could do some clever code with generics and recursive type parameters. If you don't know what that is, have a look at enum extends enum e. That's an example of a recursive type parameter. So one could do something to genericize the node and have sort of one superclass node that would then be used. But I didn't want to go that way. I tried it. I went down that a little bit down that path, and I came back because it was a bit too complicated, unnecessarily complicated. Whereas this is pretty simple. It's just basically a class which implements these methods, left, right, and value. All right. And then the other things we need to do is to delete the contains, because that's now contained within the class. Also, the iterator don't need anymore. That's done by the abstract binary tree, and the max depth is also done by the binary tree, and we don't need the pair. I noticed we also don't need the main. That was just a test I shouldn't have had there. So I'm cheating a little bit because that shouldn't have been part of the count, lines of code count. But yeah, there we go. So this is now the AVL tree done. Let's run the test, make sure that it still works. It doesn't. I made a mistake here. So I made a mistake somewhere. There's a mistake. Oh, concurrent modification exception. That's interesting. That's interesting. It should have been. I should have seen a concurrent modification exception, so I must have changed something somewhere there. So I wonder if that's in the iterator, or where it is. So this is a binary tree iterator. It's got a mod count. And when I call next, if I've got co-modification, then I'm going to, I think I know what happened. I think that we're shadowing the mod count. So if we go to the AVL binary tree, I bet there's a field. Yes, there we go. So we've got a field mod count, which is shadowing the superclass's mod count. So let's delete that. And now it should hopefully work. Okay, so now it works. So I don't like sharing fields between classes. Not my favorite thing to do, but there we go. At least it worked. All right, so the last thing we want to do is the red-black binary tree. That's the one. And this also is going to say extends the abstract binary tree. Get rid of the mod count. I'll do that from the beginning this time. I'm going to have a root method over here implemented. The root, return, oopsie, I've got changed to Greek here. Return to root and delete that. Node has to extends abstract binary tree dot node, and again we've called it T, which I don't like. I prefer to having a different name just to distinguish between them. And then we need to copy and paste the method calls here, these ones, left, right, and value, which we're going to do from the red-black tree. And you might wonder why I don't use records here, but there's a reason, and that is that I don't want to. I want to do this like that. I don't want to. The field shouldn't be final, so the fields must be changeable. And if you have a implements and extends, and if you have a record, then of course it's immutable, so we can't use that. Good, so let's go and have a look at contains can be deleted, don't need that anymore. This contains can be deleted, don't need that. We have the iterator, or the max depth can be deleted. Let's throw that away. The record can be deleted, and the iterator can be deleted. And of course the actual binary tree iterator can be yanked away as well. So we have now the red-black binary tree being quite a bit shorter, and in fact all of them are quite a bit shorter. So let's run the code and make sure that it actually works. Also, it didn't need JavaUtil anymore because the array deck is used only within the abstract binary tree. So let's run this again and see whether or not everything passes. It seems to pass. We still have the slow contains for the unbalanced tree, which is what we would expect to see. The other ones are like milliseconds, and this one is like 9 or 10 seconds. But that seems to work quite nicely. Let's have a look at how many lines of code we've got. So we've decreased by 120 lines of code. 120 lines of code, which is quite nice because it means that there is less code to maintain. And if somebody wants to write a different type of binary tree, they can very easily do so by simply extending the abstract binary tree, which should have most of the functionality built in. Not all, but most of it. And if you now run the duplicate checker, there's still some duplicate code which one could try to improve on, but I'm not going to do that. I'm going to leave it like it is now, unless I see something really serious. But okay, the avial binary tree. This is one interesting one. It says, look, rotate right and rotate left. Use duplicate code fragment inspection. I should use that one rather. They say I should use this one. Okay. Okay, I'm going to just do Java over here. And okay, well this didn't find anything to report. Thank you. So it's saying that I should fix out rotate left and rotate right is basically the same code, except one is going left, one is going right. So one could try and change that. And for this one, I actually want to do this with AI. So I said I'm not going to do AI, but I'm going to do AI for this. And let's see if we can do that with AI. I don't know if this is going to work. Write a single method that does the rotation in both directions. Let's see whether it's able to do that. Now it's generating all the other code as well. I don't want to do all that. Get balance. Rotate node, comma, is left rotation. Yeah, so this is what I was worried about. So the code that's being generated is basically going one way or the other way. It's not really what I would do. I think neither is particularly elegant. It might be better to have the I wouldn't do it like this. It doesn't seem to be. It doesn't seem to win us that much to do it this way. To have sort of the Boolean, and then if it's left, then this and that. At least this part is the same. Node height and node new root height is the same as before. But I'm not convinced this is necessarily going to win us that much. I'll just have the two methods. I think that's okay. Because what we're doing is we're reading the left, then we're reading the right, and then we're setting the right, we're setting the left, and then setting the height. I would rather have written it differently if I was going to do this, which I don't think we should. But if I was going to do it, here's what I would do. I would probably make do this quite differently with functional interfaces. So we're going to do rotation, rotate, and this would be, the one rotates, has a new root right. Let me just close this one for now. Has a new root right, and the subtree is the left, is a new root dot left, right? So that's dependent on that one. Yeah, so what you would need to do is, based on a node how would you get the new root? So you'd have to have a, let's call this just rotate. It'll be node comma a binary function, a unary function, unary operator, which of node of t, and this would be new root getter, right? And then we'd have a same type of thing for the node t for the new subtree getter, right? And then what you would do here is you'd say not node.write, you'd say new root getter dot apply node, and then you'd have the subtree being the next one would be then the new subtree getter dot apply. Oh, sorry, I got that wrong. It should be the new root. So this should be the new subtree getter dot apply of the new root. And so the one would be the call to right, the other one would be the call to left. So if you called this, for example, with the from the left, it would be, you'd say return rotate node comma, this would be node colon left. What's the first one? The first one is right, comma node colon left, right? If that makes any sense. And that would then get the, that when they do the first two, new root equals node dot right, and then that would then call the right method on your node, right? And then the other one would be the left method on your new root. So that would be the same thing as what we've done over here. And if you did the same with the rotate right, you'd just do it the other way around. So you'd have node left and node right would then be the equivalent of these two, right? So so then the other part you'd do, don't add that code, is we then need to get these parts over here. New root left equals node. So this needs to now set it equals. So it need a consumer. No, what do we need? We need a function. What do we need? A buy consumer. We need to call set left. Oh, we don't have a set method, so we don't have a method to set the value of left, right? So we don't have that. So what we would need to do is to add a left method on the root, or we can do this differently. So we can do this. We can say, if we want to have these two things done, how would you do that? Good question. So you'd have to say, I think you need a buy consumer here. Buy consumer of node t comma node t. That'll be the new root setter. Okay, and so now you'd say new root setter dot accept new root comma node. Okay, I'm doing this completely off the cuff. I've not rehearsed this or tried it out before, so if it doesn't work, I apologize. But this is what I think we should do. So if you're going left, you want to do this one over here. So it should be comma new root common node should be then new root dot left equals node. I need to call it something else. Let's just call it n. Like that. Okay. And then I'll have to do the other one. Same thing for the other one. You'd have to say n comma subtree would be n dot right equals subtree. Where this has to be, again, another node. So we'll need two of these by consumers. This will be the new node, or the node setter. And that'll be the node set over here. So basically we'll do new root setter except new root comma node. And then we'd need the node setter except node comma subtree. If this worked, which I'm highly doubtful about, then we should be able to eliminate this code and just have one rotate in both cases. So let's copy this up here as well. We'll need it slightly differently though. It's going to be new root dot right equals n, and node dot left equals the subtree. So these two. Okay, let's see whether that works or not. It seemed to have worked, the rotation, so that's pretty cool. Although I don't know if it's... let me just do one thing here. I'm going to say print out rotate right, because I want to make sure that it actually is rotating in both directions. Otherwise it's only do one and it happens to be correct, and then it's like yeah, I managed to get this code have even less duplicate code, but in the meanwhile back on the ranch it's actually okay, so we've got left and we've got right. So we've got both directions, and the answer seems to still be correct, which is great. So it seems to be correct. Let me delete this code. So we just have two rotations, left and right, and they are doing the same as before, using these function interfaces. So this is quite nice. It's a bit like function pointers used to be in the past in C or a language like that. But it seems to work quite nicely. So we have just one method that does this. The thing is it less obscure? Probably it is more obscure. I'm probably going to say it's more obscure. I'm not even sure if it's going to save code. So we were 655. Now we're 661. So we actually increased the number of lines of code because of this complicated code over here. So it didn't, and this code's also not very short. We could we could add methods to the node. So we could have methods for the right and left to set them. So we could have public void left node e left this dot left equals left. The problem with having methods so you can have method references is that also increases the lines of code again. So if you're trying to be as short as possible, then that's not going to necessarily work. Alright, so if you go back down to where this is called, the right is called, let's go down to the rotation over here. So now we could say node : left, node : right. That looks a bit neater. And but it looks funny because it's like but so I've deleted 4 lines, but I've added another 8 lines. So it's going to increase the number again. So we're going to end up with having more lines of code. The way I'm going, I'm going to go from 777 lines of code to 666 lines of code, and make people very worried about that. But So I'm not sure that this is necessarily a good idea to do this rotation in this way. I'm not convinced, because it certainly, before it was fairly, I think, fairly easy to understand. We might have like put this into a common method that does both, but even that would add lines of code. And I'm not sure what else one can do here. There's also rotate right and left there, which is being used. So it doesn't seem to be. It doesn't seem to have improved it much. But the important thing is that we've got that our tests still run, everything's still correct. So this was an experiment to try out different things. We didn't really use ChatGPT this time. But if I wanted to add a new type of data structure or new algorithm, of course I'd have a look in my clever books on the bookshelf. So I haven't memorized the whole lot, but asking ChatGPT might also be quite useful, because you can just say, hey, how would you do this? And it would maybe give you the right answer. So again, thanks for watching. Hope you enjoyed it. There are now quite a few of these live streams out there. And let me know in your comments what you think. If you give me a thumbs up if you like it, or a thumbs down if you don't like it. Tell me how I can do this better. I know that I'm going quite fast for some people. If you've not I tend to go too fast when I'm coding live sessions. So this is why I talk when I'm coding, because the talking slows me down. It makes it so I have to explain what's going on, and that usually puts a bit of a brake on it. It's like holding the brake whilst you're cycling, do not go too fast. But let me know what you think, and thanks for watching.